When the Samsung Galaxy S5 came out back in 2014, it was an absolute beast. A true flagship device, right? It had everything, a fingerprint scanner, even a heart rate monitor. But what's really fascinating is what was going on underneath that famous textured plastic bag. It was this hidden world, incredibly complex, totally divided, and as it turns out, deeply vulnerable. So today, we're going to conduct a little digital autopsy.
Because here's the thing. The most important thing you have to understand about the Galaxy S5, it wasn't one phone. Nope, it was actually two, crammed into the same body. And that dual personality, well, that was the real key to its insecurity.
All right, for our first incision, we're going to look at the core architecture. The S5's entire security landscape, its whole world, was defined by this one fundamental split. And this wasn't just a software thing. It went all the way down to the silicon. So, depending on where in the world you bought your S5, you got one of two completely different brains inside it. You either got a phone with a Qualcomm Snapdragon processor, or you got one with Samsung's very own Exynos chip. Now, why does that matter? Because it meant a completely different baseband. That's the little computer that handles all your calls and data. The Qualcomm phones used a hexagon DSP, while the Exynos models ran on Samsung's own Shannon platform. We're talking two different processors, two different radios, which means two completely different sets of vulnerabilities. It created this huge, fragmented attack surface right from day one.
And this slide really shows you just how deep that split went. I mean, we're talking about different real-time operating systems, or RTOs, and totally different communication protocols for the main processor to even talk to the modem. So a security flaw in Qualcomm's QMI, its interface, just wouldn't even exist on an Exynos phone. And a bug in Samsung's SIPI-C protocol? Totally irrelevant to the Snapdragon models. You can imagine what a nightmare this was to secure properly.
Okay, so with that really complex internal picture in mind, let's look at the first major breach. And this one, well, it didn't need some super deep hardware exploit. Instead, it took advantage of a simple, almost unbelievable mistake, right there on the surface.
This quote from the research that blew the whole thing open, it says everything. The core mistake was just downloading critical system updates over unencrypted HTTP. That's it. It was the digital equivalent of leaving your front door not just unlocked, but wide open with a welcome mat out.
And this is exactly how it worked. This attack was famously used against the phone's built-in SwiftKey keyboard. So, picture this. An attacker on the same public Wi-Fi network as you could just sit there, wait for your phone to ask for an update, and then swap out the real file for a malicious one. And the worst part? The phone's own trusted update process would then execute the attacker's code with high privileges. It was a stunningly simple oversight that put an estimated 600 million devices at risk.
So this brings us to the real cat and mouse game between Samsung and the security research community. As we go deeper into the phone, we start to run into the powerful tools used for modification and the permanent hardware-level consequences for even daring to try.
So, let me introduce you to Odin. Now, this isn't some third-party hacking tool. This is official Samsung software that was never, ever meant to see the light of day. But it leaked, and it gave developers and researchers a golden key to the kingdom: the ability to write firmware directly to the phone's core storage partitions.
But for every key, there's a lock, and Samsung's lock was the Knox eFuse. The best way to think of this is like a physical tripwire. It's a one-time programmable fuse literally built into the hardware, designed to be the ultimate judge of whether the software on the phone is authentic or not.
And here is the absolutely crucial part. If you used Odin to flash anything that wasn't officially signed by Samsung, say a custom kernel to get root access, the bootloader would detect it. It would then send a tiny pulse of high-voltage electricity to that eFuse and physically blow it. The Knox status you see here flips from a 0 to a 1, and this is key, it can never be changed back. It is a permanent physical scar on the device that forever disables high-security features like Samsung Pay. No going back.
Okay, now we're going to journey to the deepest, most critical layer of the device. This is the part you never directly interact with, but it controls all of your connectivity. We're talking about the baseband processor.
So, here's a fun fact. Every modern smartphone has a secret second computer inside of it. The baseband processor is an entirely separate system from Android. It's got its own CPU, its own specialized operating system, and its only job is to talk to cell towers. Android just kind of asks it, hey, can you make a call, or can you get some data? And the baseband does all the heavy lifting, operating completely inside a black box.
And the software running inside that black box? By today's security standards,
It was, well, ancient. These baseband operating systems lacked the most basic protections we take for granted. There was no separation of privileges, all code just ran as king. And they didn't really validate incoming data. But most critically, there was no ASLR, address space layout randomization. What that means is that all the important code was in the exact same memory location every single time the phone booted up. That makes writing a reliable exploit 1,000 times easier. The baseband was a very, very tempting target.
Now, you might be thinking, okay, the S5 is old news, but the architectural decisions and the security flaws from that era didn't just vanish. They cast a very long shadow, a legacy of vulnerability that connects in a direct line to the critical exploits we're still seeing today. This slide shows that direct lineage perfectly. On the left, we've got a bug from the S5's time, a memory corruption flaw in that Shannon baseband. To exploit it, you needed a fake cell tower. Now, look to the right, at a vulnerability from 2023 affecting modern Samsung phones with Exynos modems. It is the exact same class of bug, but the attack has evolved to be zero-click. An attacker now only needs your phone number to compromise the baseband remotely, over the internet. The ghost in the machine is still very, very much with us.
And the stakes are about to get so much higher. The next big evolution in this technology is called Integrated Sensing and Communication, or ISAC. What this means is that future modems won't just be radios for calls and data. They'll be active sensors, using signal reflections to create a sort of radar-like image of the world around you.
Which leads us to our final lingering question. The Galaxy S5 really gave us a masterclass in the complexity and vulnerability of that hidden computer that powers all our connections. So, as that computer evolves from just being a communicator into an environmental sensor, one that can literally see the world around us, how can we possibly ensure it's secure when we know its very foundation is built on this long legacy of vulnerabilities?